Okay, so just let me recall what we did in the last class. We started with something called as floating point numbers. What is the need for floating point numbers is you cannot represent decimal numbers infinitely long. For example, if you want to represent some decimal number, something like 0.123578905 likewise, you cannot keep on representing large numbers. Not only the decimal numbers, even the larger magnitude numbers, even without these decimal numbers, say 123578905 etc., you cannot represent within a given storage limited space. So there was a need to form a certain way of representing the numbers. So that is how we proposed a model where you represent a particular number using three components. That must have a sign bit, that must have a magnitude part, which include the integer and the fraction part, which uh, combinedly we call it as a mantissa, and then the exponent part. This will give you a certain range. And within the mantissa part, you need if you can able to follow a certain format, which means that any number you have, you represent it as 1 point something, or you represent it as 0.1 something, then you can always save lot of space, and at the same time you can represent large values of numbers, especially with this exponent values. You can represent huge range of numbers based on the bit size, based on the format size. So a digital format has been divided into three different components. That is, one bit is used to represent the sign, and then certain number of bits are used to represent the exponent part. So this is the one that will give you the range of values to be represented. Then you had a significant part which is nothing but the mantissa representation. And even in the mantissa representation, if you are able to if you are able to frame a certain standard, such as all numbers will have something like 1 point, or this is in decimals. In case of binary, either you will have 0 and 1, right? So either you can have 1.0, 1 point something numbers, or you can have 0.1 some numbers, which means that in the mantissa part, so this complete thing is a mantissa part. In the mantissa part, it is okay for you to represent only the portion after the decimal points. Okay, so what about the other numbers? The other numbers such as this one, 1 dot which we have proposed, or 0 dot which we have proposed, and then multiplied by this 10, whatever the formats in the standard decimal formats we have, all these things are understood by the computers and processed accordingly. So likewise, we saw one such simple model. We propose our own model, in fact. So there is no standard to this. So if we can represent a floating point number with 14 bits length, we have divided that one bit will be sign bit, and then 5 bit is for exponent and 8 bit for significant bit. We created our own set of rules. So that is, say for example, we created our rules such that it must always start with 0 point something. Okay, so which means that we are moving the decimal points towards the extreme left hand side, and then we are adjusting the exponent side. But this is in terms of decimal representation. In terms of binary representation, all we are interested in is ones and zeros. So what we do is the decimal value, we try to find out which is the closest binary value representation, and then accordingly we manipulate. So we saw different format, and they did have disadvantages. The disadvantages were they were utilizing lot of spaces here. And then one more disadvantage is how do you represent negative exponent values? You can represent 10 power 9, but what about 10 power minus 9? So all these were disadvantages. In order to avoid the above two problems, then a slight normalization was done. What is that particular normalization? Instead of you having as 0 point something, you have, sorry, 1 point something, you create a rule such that you will, all the numbers will be represented as 0.1 something. Okay. So by this method, the first disadvantage of utilizing the wastage of space was minimized. And the second disadvantage is also the representation of negative numbers. That was also minimized. And how that was, that has to be minimized, but in this particular case, it was not minimized. So how do you solve the negative exponent numbers here? So these negative numbers has to be converted into a positive number. So what is the maximum extreme negative number? It all depends on the bit size. For example, if you consider, yeah, how many bits are here? If we consider 1, 2, 3, 4, 5, 6, 7, 8 bits. If the exponent part, oh, this is the mantissa part, right? So exponent part, 1, 2, 3, 4, 5 bits. So what is 2 power 5? 2 power 5 is nothing but 32. So the maximum exponent value that you can represent is minus, it is 32. And if you want to include the negative range also, then you can represent from minus 16 to plus 16. But the problem here is, how do you represent the negative number here? So people suggested that the maximum extreme negative number in the example that I just said, which is minus 16, can be converted into the minimum positive value. What is the minimum positive thing that we can represent? You can represent it as 0. So what we do is, we add any number, this exponent value, with plus 16 value, as in this particular example. So minus 16 when added with plus 16, your minimum value will start from 0. Similarly, if you have say minus 3, you add plus 16 to it, so 13 represents minus 3. So this particular process is called as a biasing process. So which means that we included the biased exponents. Okay, so and we did an example also, right? So we took a 5-bit response, a 5-bit exponent, and then we did the example. I think this example we covered. Yeah, I think example 2 we are supposed to do. Okay, let us continue from what we completed in the last class. We need to express this particular number in a revised 14-bit floating point model. Whenever we say revised, please note that this revised includes your number must always start from 0.1 something. This is the first revision. Second revision is biasing. Yeah. Second revision is biasing. Right. So if you are asked to build in a basic model, then basic model consists of any number representation with this particular format, 1 point something. This is the first rule. And second rule is, you did not have any way of representing the negative numbers. So negative numbers cannot be represented in the basic model. Okay, in the revised model, we did this. Now, let us do this particular example of 0.0625 to be represented in a 14-bit floating point model. Now, which is the number one? This is a decimal value. First thing that you need to do is convert this into a equivalent binary value. Okay. Now, what is the closest value that is close to 0.0625? It is 2 power minus 4. 2 power minus 4, in fact, is 1 by 2 power 4. So if you find out, it will be 0.0625. Now, what is the thing we need to do? We need to represent 2 power minus 4 in 0.1 format. So if you do that, this 2 power minus 4 can be written as 1 into 2 power minus 4. This is the first step, right? So we have written here 1 into 2 power minus 4. But what is the format we need? We need a format something like 0.1 and then the values. So it is very simple in this particular case. All you need to do is move this decimal place before. So moving this decimal place before, it will become 0. Please note that if you are moving the decimal place to your left, add the number of decimal positions you have moved to the exponent values. So your decimal values now will become -4. You have moved to 1 places to your left. So add 1 to it. So this becomes 0.1 into 2 power minus 3. So we got this one. Now, then what is the revised floating model includes? First thing we have done. That is we have represented in terms of 0.1 something. Second is we have to bias the negative exponent values. So what is the biasing value? In order to find this biasing value that is required, you need to find out what is the bit size of the exponent fields. It is 1, 2, 3, 4, 5. What is 2 power 5? 2 power 5 is nothing but 2 into 2 into 2 into 2 into 2. So 2 to the 4, 4 to the 8, 16, 32. So 32 is the maximum possible. So half of that is going to be 16. So 16 is the midway value for biasing. So we need to do 16 minus, we have to subtract this number with 16. So 16 minus 3 is 13. Equivalent binary value is 0, 1, 1, 0, 1. So your exponent field has this entry 0, 1, 1, 0, 1. Okay, and this is a positive number, it is plus 0.0625. So hence your sign bit here has got 0. If it is a negative number, it will be 1. Now coming to the Mantissa part. Mantissa, what is that you have? You need not bother about the 0 point something. All you need to bother is the fractional part, the decimal part. So it is 1 and then rest all it is 0. Let's take one more example. Yeah, minus 26.625. This is in terms of decimals. First step is convert this into binary, equivalent binary. With what is the, then how do you convert this into binary? So 26 can be converted as 11010 and then dot 625 can be represented as 101 to the base 2. So we have converted into binary. Then it is the normalization process. Normalization means how many positions you are going to move. You are going to move 1, 2, 3, 4, 5 decimal places. You are going to move towards your left. If you are moving 5 decimal places to your left, then it will become 0. This 110101001. Then to the exponent part, what you must do, if you are moving 5 decimal to your places to your left, you will add so many number of positions to your exponent part. So into 10 to power 5. It is not 10 power. Why? Because we have converted into decimals. Okay. Now, so we have normalized. So that is the first step in the revised 14-bit format. Second step is we have to bias. Second step is the biasing step. So we will bias it with what is the number of fields you have. You have 5 different fields, 5 fields here. So your biasing value will be 16-bit biasing. So it is, you have to add 16 to the existing value. So 16 plus 5 is 21 equivalent to 10101. So your sign bit here, this is a negative value here. It is a negative value here. So your sign bit is 1 and then your exponent bit is 10101, this one. And then your mantissa part, the fractional part, 110 significant part, 110100101, which is represented here. Okay. So any doubt till this? Okay. Then having standardized the representation of floating point numbers, then people started that every manufacturer, they tried to create their own bit size representation. Now what is this? This is a 14-bit floating point number representation, right? Some people suggested that we must have 18 bits. Some people suggested that we must have multiples of 2. So they started doing a 16-bit floating point representation, then 32-bit floating point representation. Likewise, every manufacturer started their own way of representing floating point numbers, which created incompatibility between multiple systems. So there was a data flow mismatch also. Okay. Say for example, you ask me what is say 100 into 100, right? So if I am one robot, so I will just give you your answer as 100 into
वो थी 25% थी अटेंडेंस.
उससे देवेश से 2 मंगवाए थे.
let's enjoy the conversation.
बड़ी वाली वो भी 10 ली थी.
खत्म सारी.
सारी खत्म.
क्यों म्यूट किया भाई?
मैं था
यार
मैं जो था वो टीचर्स लेके आया था.
हाँ
बिस्किट.
हाँ.
वो पीते पीते अरे 3 फुगड़ियां पता ही नहीं लगा.
okay, somebody messaged. Why did you message? We could have enjoyed the conversation. Okay, fine. So good, Rahul. You are enjoying the class. Okay. All right. So, so that was the problem. So every manufacturer, there was a compatibility that arose because you need to send the data from one system to the other, and then the processing of the data might happen in some servers placed somewhere. So all these compatibility issue came. Then IEEE, which is a standard organization which takes care of multiple standards, they proposed two standards in fact. Okay, so what is the objective of IEEE is IEEE, their objective is to create the standards in engineering section. So the standard, the abbreviation of IEEE is International Electrical Electronics Engineers Association, in fact. So that is what is the IEEE is. So what is the name of the standard that they created was, they created a standard named as IEEE 754 standard. Okay. This standard has two, I mean, this will have, it is something like creating a law. Say, if we create a law, there will be multiple articles into it, right? So if one law is created, there will be multiple articles, multiple acts into it. So similarly, IEEE 754, they created two different standards, especially for representing the floating point numbers. One is called as a single precision floating point standard, and then second is called as the double precision standard. So IEEE 754, it consisted of two standards. One is a single precision floating point standard and other is a double precision floating point standard. Now let us focus on single precision floating point standard. So what is a single precision floating point standard is, this will have a total of uh, 32 bits, 32-bit floating point representation is called as a single precision floating point standard. And at the same time, what is the biasing value? The biasing value was going to be 127. And how did you get this 127? Obviously, you can have an 8-bit exponent value. What is 2 power 8? 2 power 8 is nothing but 128. So your exponent range, the biasing range will be, it is not 127, sorry, it will be 256. Okay, so half of 256 is going to be 128, right? So the biasing value is going to be 127. Okay, excluding the zero. So 127. So that will be your biasing value. Now, what is the double precision? I mean, as the name itself implies, this is a single precision value and double precision value. Means the precision is going to be much larger. So this one is going to be 64-bit representation. So this is a 32-bit representation here. Double precision standard is a 64-bit representation. In 64-bit representation, 11 bits are used for exponent, whereas here you are using only 8 bits for the exponent part. Here you are using 11 bit for the exponent part. Here in single precision method, you are using 23-bit significant size, whereas here it is a 52-bit significant size. Okay, and if you are having 11-bit exponent, the biasing value will be 1023 is the biasing value. So here it is for an 8-bit, it is 127 is the bisegment. Now, what is the difference between whenever you are being asked to represent any floating point number in IEEE standard, always first go in for single precision method. If you are doing hand calculations, the single precision method is fine. Unless otherwise specified, then only you go for double precision standard representation. Otherwise, you can stick to single precision standard method. Now, what is the difference between the IEEE's method? Now, I am generalizing. I am not saying single or double. What is the difference between the IEEE's method and the simple method that we proposed? Right? We earlier proposed that there are certain rules that we proposed, right? Now, what did IEEE said? IEEE said that your significant has will have one to the left of the radix point. That is, you will always have your number represented as 1 point some numbers. Whereas in our simple model, how did we represent? First, we represented as 1 point something. Then later on in the revised model, we represented as 0.1 and then something. Right. So IEEE ignored these things, and they said that you are in an IEEE standard format, you must represent your number as 1 dot something. Okay. Now, as an example, maybe let us see 4.5. How this what is the equivalent value of 4.5? If you represent this 4.5 in a simple model, we used to represent it as 0.1 something, right? So it is 0.1001 into 2 power 3 in a simple model. Whereas in an IEEE model, any number will be represented as 1 dot and then the number. So it is 1.001. It is not 10 power 2. It is 2 power 2 in an IEEE format. Okay. And here, what is the exponent value? The exponent value is going to be 0, 1, 0, and significant value will be 0, 0, 1. Okay. Now, and why did IEEE do this? Why did IEEE do this is, in the earlier method, we are doing this particular format, that is 0.1 and then something, which means that the 0 doesn't have any value. If you consider a hardware representation of a 0, it means that it is like a switch. You are having a switch, but it is in an open position or it is in an off position. That is what 0 represents in hardware. Now, which means that though this representation is good, but we want to improvise on saving the data. Instead, if you can, if you are representing 1 dot something and if you are ignoring this one, it means that you are saving the data that is required to store 1, right? So if you create this 1 dot as a standard one, then it means that the advantage or the faida that you have here is 1 need not be stored explicitly, right? So compared to the simple model, so we are saving 1 bit of storage in IEEE. Right. So if you are saving 1 bit of storage in IEEE, just imagine how many calculations you are making, right? When you are running a loop of 100 using a for loop or anything, and every time it is calculating this 1 dot something, you are ignoring that one, meaning you are saving so much amount of space, and at the same time you are improvising your computation speed also. So this is the advantage of having 1 dot the value representation instead of 0 dot something. Now let us do a very simple example. Express minus 3.75 as a floating point number using IEEE single precision method. In this particular example, they have specifically given that it is a single precision method. At times, what you might see is represent in IEEE format. So if it is an IEEE format, assume that it is a single precision method unless otherwise specified that it is a double precision method that is required. But what is the, since you are doing a manual work, what is the disadvantage of a double precision method is you have to create 64 bits. Instead, creating a 32 bit is slightly easier, manually at least, rather than 64 bits. So that is the reason. Okay, now let us come back to the example. So it is 3.75 as a floating point number in IEEE. First, let us represent 3 in, so let us first convert this into binary. So this is a decimal value here. This decimal needs to be converted into binary. That is the first step. So 3 is 011, that is what is the integer part is, and 0.75, you keep on multiplying it by 2, it is 1.5, so the base is 1, again multiply it 1, the base is 1. So let us consider just 2 bits per time. If you want, you can continue. I mean, this will not continue also, because you get 1.0, you have taken a base of 1, so you get 0 only. 0 multiplied by anything is going to be 0. So your decimal part is just 0.110000, etc. So you need to represent minus 3.75. So minus 3.75 is minus 11.11. Now let us do the normalization. Now, how do you do the normalization? Normalization is nothing but moving the decimal bits according to the required format. Since the required format is IEEE here, it is this decimal place 1 needs to be moved one position to your left. If you are moving one position to your left, then you will add 1 to your exponent part. So it is minus 1.111 into 2 power 1. Now, since this is a IEEE we are a single precision method, what is the biasing value? Biasing value is, at least this biasing value you need to remember. This biasing value is 127. This double precision's biasing value is 1023. So your biasing value was 127. All you need to do is add 127 to your exponent value. So it is 128. So how is 128 represented in binary values? It is represented as 1 followed by 7 zeros. 3, 4, 5, 6 and 7 zeros. So because this is an 8-bit representation, right? So this is an 8-bit representation. So now coming to the format, you may count that there will be 32-bit representation. Okay, so your first bit, which is your sign bit here, your first bit, which is your sign bit here, is 1 because this is a negative number. And then your exponent bit is 1 followed by 7 zeros. This is an 8-bit representation. So 8 plus 1 is 9 bits. 9 bits are done. Out of total 32 bits, 32 minus 9 is 20. 3 bits are remaining. So what is the integer, the mantissa part, or the significant part? Significant part is 111 and then rest all zeros. So it is 111. Out of 1.111, we are considering 1111 because this one dot is already implied. It is already implied in the format. So rest all it is 0. You may count here that it must be 23 bits. So let us see if I have made a mistake. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 and 23 bits. All these are this bit size, this field size is 23 bits. Okay. Now, if you want to recover the value, because this is how you represent in terms of binary, you must also know how to recover the value, right? So how was the recovery process done? So first look from, let me erase the writings that I have done. Yeah. Now what I'm going to do is I'm going to recover from the format. Now that this is given, how do I recover what is the implied value? So first the sign bit is 1. So I put minus. Okay. And then one dot is already implied, right? So one dot is implied. And then what is the value I'm having? It is 111. It is 111. And then since this is a binary representation, it is multiplied by 2 is also implied. Now the power value, what is this particular power value? Power value corresponds to 1 followed by 8 zeros. And what is that equivalent to? It is 128. This is a biased value. So if I want to get the original value, I have to subtract 127 to it. So my actual value will be minus 1.111 into 2 power 1. If this 2 power 1 needs to be removed, I need to move the decimal places to my right now, and so that I will make this as 0. So it will be minus 11.11 into 2 power 0. So what is minus 11.11 equivalent to? It is equivalent to 3.75. Okay, so this is how you recover. See, as engineers, you must also know how to represent a particular number in binary floating point format, and how do you recover a number from a floating point representation is also required. Okay, so and there are additional things that you need to know. If especially in a single precision representation, you know that the total value that are represented, the exponent value, if it is 255, that which means that if all the bits of your exponent value are 1111, then it means that the floating point is representing a value equivalent to plus or minus infinity. I mean, you might have noticed when you program, right? You will get NaN number, or you might get an invalid number or infinity number, INF. You might have come across this particular term INF when you are doing some program. You might have come across this number. This represents not a number, right? So how is these things generated? How is these things generated is whenever you go beyond, what is this exponent? It is exponent is 2 power, say I want to represent 2 power what 320. Obviously there is a limitation on this size, right? So the maximum that you can provide is 2 power plus 127. Right. So if it goes beyond plus 127 means you will always bias it, right? So you will always bias it with one more plus 127, which means 2 power 254 is the maximum. So if your calculation output results in a value which is equivalent to something beyond this, something like this 2 power 320, then automatically your maximum value is set to 11111, representing that your output will be shown as an infinite value. Similarly, if you are doing complex calculations, so if you are doing um, some complex multiplication or something which is not result, even in calculators you might come across that if you are doing a wrong calculation, you will get an error value. How is that it is generated is 1 minute. Okay, just accidentally it moved away. Okay, so if all your exponent values are 1111, and then your significant bit has got alternate ones and zeros, then you will see an output representing that it is not a number. This is for a single precision. For a single precision, your total bit size is only 32 only. But whereas in case of a double precision, your total value will be 64 bits. In that particular case, the format of getting is slightly uh, different. So in both, yeah. So an exponent value of 2047 will be this is a special value instead of 255. So here the equivalent value for 1111 is 255, right? In that particular case, since you are having 11 bits, what is 2 power 11? It is 2047. So 2047 is the special value that will represent the infinity and not a number value. Now in 14 point floating point representation, you do have plus zeros and minus zeros also. So if you are having plus 0, then all the bits are zeros. If you are having minus zeros, then except the sign bit, all the bits are 0. So sign bit is 1, representing that you are having a negative 1. So as programmers, you must know that when are you getting minus 0 and when are you getting plus zeros. So you should not consider, you must always program the way you write your program, you must make sure that you must think in terms of hardware. If you are writing a line, how is this executed in the hardware part? So that is why you must also learn machine languages. Unix is a good platform that will help you understand the machine languages. In olden days, we had MS-DOS, DOS. So that is all kind of a machine language. Even microprocessors and microcontroller programmings, they are all machine languages, which means that the one that computer understands, the one the programmer thinks in terms of hardware. Okay. So minus 0, obviously it is not equal to 0. Hence, programmers should not test for zeros in your programming. Okay. All right, so let's do simple examples and then we will move on to the next part. So convert a decimal number to IEEE 754 single precision representation. Obviously, single precision representation is nothing but a 32-bit floating point notation. So the given number is 263.3. First step you do is convert this into binary. Okay, so I am not doing the binary conversion, but I am giving you the answers. So the binary representation is 100 likewise, and then the uh, 0.3 can be represented as 010011 etc. Now you have to create normalize this. What is the normalization process? Normalization process is the second step after converting to binary. So you have to move your decimal places. How many positions you are going to move? Please note that it is a one dot format in IEEE. So you are moving 8 different places. I have already written here. So it is 8 different places. All you need to do is multiply it with 2 power and add 8 to the power. So 0 plus 8. So it is 2 power 8. So we have got the scientific IEEE notation. Now in it is a single precision representation. So totally there will be 32 bits. So your sign bit, where it is a positive number, this is a positive number here. So your sign bit will be 0. So your sign bit is 0. Your 8 exponent bits, you have to bias it also. Please note you have to bias it. So the what is the biasing value? 127 is the biasing value. You have to add 127 to it, which is nothing but 135. So 135 here can be represented as 1000111. And then your 23 fractional bits. So these are the 23 fractional bits. Continue to represent how much ever you want, but within the 23 bits. So this number is represented as it is here. This is how, so your final answer of representing and this 263.3 in IEEE 754 notation is this one. Any doubt here? Okay. Next example is a recovery of the given values. So first, this is the fields that are given to you. You have to recover the actual decimal value. So first it is a sign bit. So the sign is a positive number. And then one dot is implied. And then the number that will follow will be the fractional bits here, which is nothing but 0, 1, 0, 1 and rest all zeros. Okay. I have just copied from here. Multiplied by 2 power, we have to find the exponent values. What is this value equivalent to 100,00110? What is this value equivalent to? Was this value is equivalent to, I'm not calculating, I'm just using the, okay, it is going to be 134. Okay. Now we have to, if you want to get the original number, we have to subtract from 127. So 1.0101 multiplied by 2 power 7. Right? 2 power 7. So what is the equivalent decimal value of this? The equivalent decimal value of this we need to find out, I think. Yes. Okay. Now, right. So this is your in your binary format. This is in your binary format. Now you need to convert this into the decimal format. Okay. So convert this into the decimal format. So you know how to convert binary to decimal, the including the fractional numbers, right? So it is equivalent to just multiply it with their positional weights. So you get the fractional part, you get 0.65626. So 1.65626 is equivalent to 212 to the base 10. This is how you recover any number from the given format. Any doubt in floating point numbers? Okay. So your second problem set is based on the representations only. So try to complete the same, and if you have any doubt, let us discuss the same on Monday's class. So you have 2 days break. I think you can definitely complete the problem set. Okay. Now let's move on to the arithmetic operation, which we left 2 classes before. We obviously we started off with the uh, binary addition and even subtraction also we completed, we were doing the overflow condition. Yes. Now, what are the conditions when we do have an overflow condition? When you are representing the subtraction is, why did we go for this overflow condition is because the borrow that we are having here will alter the sign bit, because obviously the first bit is always a sign bit. The borrow that you are bringing here is will alter the sign bit. So because of that, you will get an incorrect answer. In this particular example, so we are doing an addition here. I mean, this is an yeah, where is, yes, in this particular example, you can see here that there is a carry that is being generated here that will alter your actual value, right? So this happens because of the overflowing condition. So what is an overflow condition is when you are adding two numbers and their sum, if they exceeds the actual magnitude, an overflow will occur. That overflow will change your sign bit and thereby resulting in an incorrect answer. Okay, so how to overcome this particular problem of overflowing? Now before that, you must know when will this overflow will occur. When will this overflow occur? Say for example, I'm adding two numbers, plus 12 and plus 94. Okay, so what is this addition? It is 6, 0 and 1 and plus. Please note here, this 1 needs to be accommodated, but already this 1's position, you are having a sign bit here, so that will alter. Similarly, if you are doing minus 10 and minus say minus 20, let us consider, and minus 85, again the sign bit is getting altered here because this will be 105. I need to have negative, but this one will come as a carry which will alter your overflow value. Hence the conditions at which you will overflow will occur is when you are adding two positive numbers, your result will be a negative number. When you are adding two negative numbers, your result will become a positive number. But when you add two numbers, your result must be positive, right? And at the same time, when you add two negative numbers, your result must be negative. But this overflow will alter your result, changing from negative and positive respectively. And the other condition, what will happen is if your sign bit of the result and the sign bit of the two operands are different signs. What do you mean by that? If here you are adding, or in other words, let us uh, take an example here. If you have 1 in an MSP, it indicates that you are having a negative number. After adding two positive numbers, your MSP will become 0. Why? Because let me take one example from here itself. I think we have taken, yeah, two positive numbers. Yeah, not this one. Yeah, we are having two positive number, right? So, okay, the example is not appropriate. Okay, we'll see example before that example is not appropriate. Yeah, we do have enough examples. So you must note that whenever you are doing a two positive number or two negative numbers, your sign bit is altered. At the same time, you must also note that your sign bit, your overflow will never occur if you are performing addition with different sign values. If you are adding minus 25 with plus 10, your overflow will never occur in such kind of a problem. If you are adding plus 75 with minus 10, then overflow will never occur, which means that overflow will never happen when adding numbers of different signs. Okay, so now let us do the subtraction part. Here maybe you will understand here. If you want to subtract minus 6 minus of minus 13, then how do you perform this subtraction is, obviously we are going to perform these subtractions using the complements form. Though we have extensively covered the subtraction part using complements, Here also we will touch upon the complement representation, because what we have seen before, if you just recall, we started off with arithmetic operation, we did the additions, now we are doing subtractions. So how do you perform the subtraction? We will perform the subtraction using the R's complement form. Since this is a decimal value, decimal value means the complements that are possible are nines complement or tens complement are possible. If you convert these things into a binary number, then ones complement and twos complements are possible. So here the second method is followed here. What is that? We will represent these numbers in binary, and then we will take the complements, and then we will convert it back to decimal. So plus 6, we know that it is 0, 1, 1, 0. Minus 6, the complement of everything. So 1, 1, 1, 1, 0, 1, 0 is minus 6. Similarly, minus 13 is 111 0011. Now we have to subtract these both. So please note that this is minus 6 and this is minus 13. Now normally what we do, we will do subtraction by addition. If we do subtraction by addition, then this minus needs to be converted to plus. Meaning, if you create a plus here, then this has to be subtracted. We do now, I'll take another example. We do 5 minus 10 as 5 plus minus 10, right? Similarly here, if we convert this to plus, then this becomes minus. So the subtraction is converted to plus. So again, one more complement. So complement minus 13 now, if you want to represent it as plus 13, will become, take the complement of this 0, 0, 0, 1, 1, 0, 1. We are back to plus 13 value. So what do you understand here is complement of a complement number is nothing but your original number. So what will be the final answer? Let us add. So it is minus 6 is represented as a complemented value. One's complement value 111 1010, and plus 13 is represented as this, and all you need to do is addition. So 1, 1 here, 0 plus 1, 1, 1 plus 1, 0, 0, 0, carry, and then there will be a 1 carry. Now, always when you are doing the complement subtraction, the carry is discarded. So the result is going to be plus 7. So why plus 7? Because the first bit is a positive number, which means the first bit is 0, telling that you are having a positive number, and the equivalent decimal value of 111 is 7. Obviously here also you can find out the answer. The answer is going to be plus 7. Okay, right. So this is how you perform the subtraction using complement form. Now we are going to repeat the complements for some time. Uh, Maybe since this is already time 2:50, we will continue this complement subtraction in the next class. Any doubts so far? Okay. So if there are no doubts,